This is SpaceTime, Series 24, Episode 3. Coming up on SpaceTime, discovery of a strange signal from Proxima Centauri, Israel's ambitious new plans for a moon mission, and planet Earth moves into Perihelion, its closest orbital position to the Sun. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists at SETI, the Search for Extra-Terrestrial Intelligence, are trying to understand a strange signal which was detected by the Parkes radio telescope and which originated from the Proxima Centauri star system. The mysterious signal, which has so far defied any explanation, was found at 982.002 MHz, buried in stellar flares erupting from Proxima Centauri. Located just 4.25 light-years away, Proxima Centauri is the nearest star to the Earth other than the Sun. Astronomers have so far detected 2 exoplanets orbiting the star, one of which, Proxima b, is a terrestrial world about 1.2 times the size of the Earth on an 11-day orbit in the star's habitable zone. That's the area around the star where temperatures allow liquid water, essential for life as we know it, to exist on a planet's surface. The other exoplanet, Proxima c, has roughly 7 times the mass of the Earth and has a far more frigid 5.2 Earth-year orbit around the star. Proxima Centauri is a small spectral type M red dwarf star, about 1/10 the mass of the Sun. It's part of the triple Alpha Centauri star system, which consists of 2 stars similar in size to the Sun, Alpha Centauri A and B, which orbit each other, and then Proxima Centauri, which orbits the pair. Red dwarf stars tend to erupt in stellar flares fairly regularly, and these flares would irradiate the surface of any nearby orbiting planets. The astronomers at Parkes were studying one of these eruptions on April 29, 2019, to understand exactly how these flares were affecting Proxima b, the habitable zone exoplanet orbiting Proxima Centauri. As part of Russian tech billionaire physicist Yuri Milner's breakthrough LISTEN initiative to search for alien signals coming from nearby stars, the astronomers at Parkes routinely pass any interesting observations onto their counterparts at SETI. The data block on the flare, which contained some 26 hours of information, was passed through SETI's filtering system, which is designed to pattern match and remove known phenomena. Now usually this pretty well eliminates everything. Except this time it didn't. What was left was a mysterious unexplained signal at 982.002 MHz buried in the stellar flare eruption. It's the first signal ever to pass through all of SETI's established filters. It's now being described as the most significant signal detection since the WOW signal back in 1977, which, as we discovered late last year, turned out to be likely coming from a system hosting a Sun-like star. The new signal, which has been named Breakthrough Listen Candidate 1, or BLC1 for short, has a consistent one-note tone without any modulation or discernible patterns. It occupies a very narrow band of the radio spectrum which is typically clear of transmissions from human spacecraft, and there's no known way to naturally compress the electromagnetic energy into a single bin in frequency such as this one. Interestingly, the signal is drifting, changing very slightly in frequency, which could be due to Earth's orbital motion or that of the source. But the problem there is that should cause a drop in frequency. But rather unusually, BLC1 is going up. Also, Parkes originally picked up the signal several times during its initial observation, but more recent follow-up observations have failed to pick up the signal again, further adding to the mystery. So what is it? Well, scientists think it might be an as-yet unknown exotic quirk of plasma physics, but an unidentified human source is far more likely. As for alien intelligence, well, that's even less likely. But to make sure, months of further analysis are planned to definitely rule out any other potential sources. To find out more, Andrew Dunkley is speaking with astronomer Professor Fred Watson.
What we are talking about here is something that I think astronomers have suspected for a long time, and it relates to the commonest form of stars that there are in our galaxy, and that is something called M dwarf stars, which you can think of as things significantly smaller and cooler than our sun, which of course, radiate less intense radiation because they're not as big, so they're not shining as brightly. And the key thing here is that they make up something like 70% of all the stars in our galaxy. So they are really, really prolific. And in fact, the nearest star to us, Proxima Centauri, which is part of the Alpha Centauri system, 4.2 light years away, that is an M dwarf. It's one of these stars which are the commonest in the galaxy. So people have suspected that whilst we've detected many planets around M dwarfs, because they're actually easier to find around an M dwarf because this parent star is not, blinding you with its own brilliance, even though we know lots of planets around M dwarf stars, they might be not in a good place because it has been known for a long time that M dwarf stars have quite bright flares, stellar flares, which send copious quantities of subatomic radiation out into their vicinity. And the suspicion has been this might be bad for any kind of life forms evolving on a planet around one of these M dwarf stars. And that's a good point, which in a sense has now been confirmed, because what has happened is that astronomers, and some of them are based here in Australia, they have detected radio burst signature, which you measure with a radio telescope, actually is telling you about flares. These things the radio bursts are something you can monitor, and what it's doing is telling you literally about the space weather around one of these stars, or actually any star outside the solar system, any star in our galaxy, which most commonly are M dwarf stars. So we've got the wherewithal to measure their radiation, which we didn't have before. That is the good news. The bad news is, it's not so good. There are lots of them, very intense blasts of plasma coming from these stars, which might well be a very bad thing for any life forms on planets around them. And the research on this, which, by the way, does have a strong Australian content, CSIRO, the University of Western Australia, Curtin University, they're all in Australia, and University of Colorado, and University of Wisconsin, Milwaukee.
It's where the cheeseheads live.
I'm not going to make any comment on that, just to move on to say that there's also a contribution from the University of California, Berkeley. There you go.
I wasn't being rude. It's a term of endearment if you're a cheesehead.
Is it? Oh,
yeah.
It's not one of those football things, is it?
Yeah, it is.
There's nothing endearing about football, Andrew.
Fair enough.
Yeah, so a multinational collaboration which has detected, the fact that, yes, we're right, we might have problems with any kind of life forms trying to evolve on a planet of a red dwarf. And in fact, the research points specifically to the two known Earth-sized planets, or two suspected Earth-sized planets, which are orbiting Proxima Centauri. They're maybe not Earth-sized, perhaps Earth-like is better because they're thought to be rocky planets. And they're thought to be within the habitable zone of Proxima Centauri, which is where you can get liquid water, as you know. So that's great. You've got all that, but then you've got these horrendous solar flares being slung at you periodically from the parent star. And that's why this is not really a good news story in the quest for life beyond the solar system.
Although the positive being that if these dwarf M-class stars exist in such massive numbers, but the proximity of the planet to the star to be in the habitable zone puts it too close because of solar flare activity, then we only have to look at 30% of the stars to find life, really.
Yes, that's right, which are harder to detect. Or the planets of them are harder to detect. Although these days, with the TESS spacecraft, the former Kepler spacecraft, and the role of amateur astronomers now who have got sufficiently precise equipment with their telescopes that they can measure this tiny dip in the brightness of a star caused by a planet going past. So we've got a lot to go by. So yes, I take your point. So the other 30% are probably the place to look if you want to look for living organisms.
Yeah, these dwarf M-class stars sound like they are probably not somewhere you'd like to be orbiting.
Yes.
in terms of planetary habitation. I mean, our star does the same thing, but we are far enough away for it not to be a massive issue. Although from time to time, we do have problems with solar flares and coronal mass ejections, and the big worry is that now that we are living in a digital world and rely so much, almost 100% on electronics around the globe now, we could get an electromagnetic pulse of such significance that we could find ourselves in very big trouble in a very short period of time.
Indeed, that's right. In particular, the Carrington event, which was, in 1859, I think, if I remember rightly, which fried all the primitive electronic communications.
Telegraph.
Yes, that's right, the telegraph. Something like that would certainly upset both our power supplies here on Earth, because it trips out it overloads the transformers and trips out their fail-safe mechanisms, but also, as you say, the digital era, especially with spacecraft up there above the atmosphere, they're feeling the full brunt of this. Fortunately, our sun does not chuck out as horrendous solar flares as M-dwarf stars do, but it's still bad enough. You can get them from time to time, and your warning is well taken.
Would we get a warning, though, if something like that were building up? Is there any way of telling that it might be happening?
Yes, so that's one reason why we've got such a flotilla of satellites in orbit around the sun at the moment, monitoring all these things. And there's a new solar telescope, a 4-meter telescope dedicated to looking at the sun, which is on the mountain Haleakala on Maui in the Hawaiian Islands. That is also interested in understanding the way it's all about magnetic fields in sunspots and things of that sort, the way these magnetic fields kind of build up and then twang, and in doing that, they, as they release themselves from the surface, they spread these high energy particles throughout space. So you can get some warning, and I think as time goes on, we'll be better equipped to do that, which is just as well, given what you've just said, that we are very vulnerable with the electronics that we use today.
We should just sort of sheet everything in lead and be done with it.
Yes, that's right.
Would that work?
Look, I like the steampunk solutions, and lead's one of them. There's no doubt about it.
There you are. Okay. Yeah, it's good stuff, lead.
Oh, yeah.
That's Dr. Fred Watson, an astronomer with the Department of Science, speaking with Andrew Dunkley on Space Nuts. And this is Space Time. Still to come, Israel's ambitious new plan for a moon mission, and astronomers see a comet transitioning between families. All that and more still to come on Space Time. The Israeli non-profit initiative SpaceIL have announced plans for another attempt to land a spacecraft on the lunar surface. Just over a year ago, the Bereshit or Genesis spacecraft built by SpaceIL in cooperation with Israeli aerospace industries crashed as it attempted to land on the lunar surface on a scientific mission. Had it succeeded, it would have been the first private company to land a spacecraft on the moon, a feat only achieved so far by government agencies from the United States, the Soviet Union and China. The new Genesis 2 mission will launch in 4 years and will include 3 spacecraft, an orbiter and 2 landers. And this time round, SpaceIL won't just have the backing of Israeli aerospace industries, but also the country's science ministry and the National Space Agency. And 7 other countries, including the United Arab Emirates, have also expressed interest in becoming partners in the project. This is Space Time. Still to come. A comet discovered last year providing new clues about how these icy worlds are moved into orbits which bring them into the inner solar system and close to the Earth. And later in January SkyWatch, the Earth moves into Perihelion, its closest orbital position to the Sun. All that and much more still to come on Space Time. A comet discovered last year is providing new clues about how these icy worlds are moved into orbits which bring them to the inner solar system and close to Earth. The newly discovered comet 2019 LD2 Atlas is a centaur, but is actively transitioning into a Jupiter family comet. Centaurs are icy bodies in unstable orbits circling the Sun in the outer solar system between Jupiter and Neptune. They're thought to start their lives as trans-Neptunian objects in the Kuiper Belt, a ring of frozen debris, comets and icy worlds orbiting the Sun out beyond the orbit of Neptune. As they move through this dark outer rim of the solar system over millions to billions of years, they occasionally, gravitationally or sometimes physically, interact with other bodies, which can cause them to slowly begin leaking into the centaur population. Once they become a centaur, their orbits often cross the orbits of the giant outer planets, Jupiter, Saturn, Uranus and Neptune. And the massive gravitational perturbations of these encounters fling these cometary bodies either out of the solar system entirely or onto new orbits towards the Sun, in the process becoming so-called Jupiter family comets. Now, this is a process that can take a few million to tens of millions of years. Jupiter family comets are short-period comets, usually with orbital periods of less than 20 years, and their orbits are primarily dominated by the gravitational influence of Jupiter and the Sun. The study's lead author, Jordan Stekeloff from the Planetary Science Institute, says 2019 LD2 is at a sort of dynamical gateway, which will see it transition from being a centaur to becoming part of the Jupiter family of comets. This dynamical gateway is a region beyond Jupiter extending to just inside Saturn's influence. Now, previous work by Stekeloff and colleagues found that the majority of Jupiter family comets first pass through this dynamical gateway as centaurs immediately prior to transitioning into Jupiter family comets. Currently, there are a handful of objects in this gateway region, including LD2. The findings, reported in the Astrophysical Journal Letters, suggest that LD2 is most likely still extremely pristine in its chemical composition. Now, although it might have lost some of its volatile ices such as carbon dioxide in the outer solar system, having not visited the inner solar system yet means it's unlikely to have lost any of its water ice. And that means LD2 presents a unique opportunity to observe how pristine Jupiter family comets behave as their water ices begin to sublime for the first time and drive comet-like activity, creating a halo, or coma, and generating its tails. Stekeloff says, based on his calculations, LD2's transitions are likely to finish within the next 40 years. Now, that's the blink of an eye in astronomical terms. And it means that scientists around today will be able to follow this object all the way through its transition into a Jupiter family comet. Stekeloff says this is important research because scientists love to categorize things, putting them into well-defined boxes. Part of modern planetary science is about understanding why these categories exist in the first place. For example, why there are active comets and inactive asteroids, and why do some objects seem to fit in multiple boxes. Centaurs and main belt comets can look both asteroidal sometimes and cometary at other times. Crucial to understanding how these categories of objects came about is understanding the processes they experience and how they've evolved over time to become the objects seen today. And this is where LD2 comes in. It represents a unique opportunity to investigate the connection between Jupiter family comets and centaurs, to understand both how they're different and how they're similar. This is SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for January on SkyWatch. January is the first month of the year in the Julian and Gregorian calendars. The name originates in the Latin word for door. That's because January is the door to the new year and an opening to new beginnings. The month is conventionally thought of as being named after Janus, the mythical Roman god of beginnings and transitions. But according to the ancient Roman farmer's almanac, it was actually Juno who was the traditional god of January. Of course, from an astronomical point of view, January marks Earth's closest orbital position to the Sun, Perihelion, which occurs about 2 weeks after the December solstice. Planets, including the Earth, don't orbit the Sun in perfect circles, but rather in ever-changing elliptical orbits. The shape of these orbits vary due to gravitational influences from other planetary objects. And in Earth's case, that especially includes the Moon, which is almost massive enough to be considered a binary partner. So, over a roughly 100,000-year cycle, Earth's orbit changes in shape from almost circular to far more elliptical. This difference is known as eccentricity, and the nearest point in Earth's orbit around the Sun is called Perihelion. Now, this year's Perihelion occurred on Sunday, January the 3rd at 10 to 1 in the morning Australian Eastern Daylight Time, when the Earth was just 147,093,163 kilometres from the Sun. That was 8:50 a.m. on Saturday, January the 2nd US Eastern Standard Time, and 13:50 on Saturday afternoon Greenwich Mean Time. Around 6 months later, and about 2 weeks after the June solstice, Earth will be at its furthest orbital position from the Sun, a location known as aphelion. Okay, let's start our tour of the January night sky by looking to the northeast, right next to the constellation Orion, where you'll see the brightest star in the night sky, the dog star Sirius. So called because it's the brightest star in the constellation Canis Major, the big dog. The name Sirius actually means scorching or brilliant, a clear reference to its spectacular brightness in the sky. As well as being one of the nearest stars to the Sun at just 8.7 light-years, it's also intrinsically bright, and almost twice as bright as the second brightest star in the night skies, Canopus. A light-year is about 10 trillion kilometres, the distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Sirius is the fifth closest star to the Sun, and it's gradually moving closer to the solar system. So it'll steadily increase in brightness over the next 60,000 years, after which time it will begin moving away again, and it will gradually become fainter and fainter. But it will still continue to be the brightest star in Earth's night sky for at least the next 210,000 years. Sirius is a binary star system comprising a spectral type A main sequence white star called Sirius A and a small white dwarf companion Sirius B, which orbits between 8.2 and 31.5 astronomical units away from the primary star. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres. Main sequence stars are those undergoing hydrogen fusion into helium in their core. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue white stars, then spectral type A white stars, spectral type F whitish yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive stars known are spectral type M red stars. Each spectral classification can also be subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and a Roman numeral to represent luminosity. Now put all that together, and our Sun becomes a G2V or G25 yellow dwarf star. Also included in the spectral classification system are spectral types LT and Y, which are assigned to failed stars known as brown dwarfs, some of which were born as spectral type M red stars but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest stars, those spectral type M red dwarfs we talked about before, which are about 75 to 80 times the mass of Jupiter, or around 0.08 solar masses. Brown dwarfs don't have enough mass to build up the sorts of temperatures and pressures in their cores needed to trigger the nuclear fusion process which makes stars like our Sun shine. Sirius A has at least twice the mass of the Sun and is about 25 times more luminous. The Sirius binary system is between 200 and 300 million years old, quite young by astronomical standards, and it originally consisted of two bright spectral type A white stars. The more massive of these two stars, Sirius B, consumed its resources and became a red giant before shedding off its outer layers and collapsing into its current state as a white dwarf around 120 million years ago. A white dwarf is the stellar corpse of a Sun-like star. Having used up its nuclear fuel supply, fusing hydrogen to helium in its core, it expands into a red giant as it fuses helium into carbon and oxygen. Now, bigger stars can fuse progressively heavier and heavier elements, but low-mass stars like the Sun simply aren't big enough to fuse carbon and oxygen into heavier elements, and so they turn off. Their outer gaseous envelope separates and floats off into space as a spectacular object called a planetary nebula. What's left behind is a super-dense white-hot stellar core about the size of the Earth called a white dwarf, which will slowly cool down over the eons of time. Our Sun will become a white dwarf in about 7 billion years from now. 5,000 years ago, the ancient Egyptians looked at Sirius and they saw it as the god Anubis, lord of the underworld, who had the head of a dog and who invented embalming, the funeral rites, and who guided one through the underworld to judgment, where he attended the scales during the weighing of the heart to determine one's fate in the afterlife. Anubis was later replaced in Egyptian mythology by Osiris as the lord of the underworld, and Sirius became the goddess Isis. By carefully watching Sirius's movements across the sky, the ancient Egyptians determined that it would be visible every night for 295 and a quarter nights, followed by 70 nights of absence. And this allowed them to determine that a year was 365 and a quarter days long. Their calculations were accurate to within 11 minutes. The helical rising of Sirius also marked the annual flooding of the River Nile in ancient Egypt and the hot, sultry dog days of summer for the ancient Greeks. In Greek mythology, Sirius was the dog star and the canine companion of Orion the hunter. Helical rising refers to the first time of the year when a star becomes visible above the eastern horizon for a brief moment just before sunrise. It's been claimed that the Dogon people in Mali in Western Africa have ancient stories describing the 50-year orbital period of Sirius and its companion white dwarf, which predate the white dwarf's discovery by modern astronomers. It's also claimed that these legends were handed to the Dogon people by ancient aquatic space travelers who told them of the third star accompanying Sirius A and B. However, a report in the journal Current Anthropology raised serious doubts about whether the stars referred to by the Dogon people were in fact Sirius A and its white dwarf companion. That's because senior Dogon claim the story actually refers to a different grouping of stars. Also, other researchers have pointed out that the Dogon could have heard about the discovery of Sirius's companion and then simply incorporated it into their mythology in 1893 when a French expedition arrived in Central West Africa to observe an April 16 total eclipse and were overheard discussing the discovery. Looking due north just above the horizon this time of year, and you'll see the bright yellowish star Capella, the brightest star in the constellation Auriga the Charioteer. Capella is the Latin term for a small female goat. The star's alternative name is Capra, which was more commonly used in classical times. Although it appears to be a single star to the unaided eye, Capella is actually a system of 4 stars in 2 binary pairs. The first pair comprises 2 bright yellow giant stars, both of which are around 2.5 times the mass of the Sun. Having exhausted their core hydrogen supplies, both stars have cooled and expanded out to become giants, moving off the main sequence. Designated Capella AA and Capella AB, they're in a very tight circular orbit, some 0.76 astronomical units apart, orbiting each other every 104 Earth days. Capella AA is the cooler and more luminous of the two, with some 78 times the luminosity and 12 times the radius of the Sun. Known as an aging red clump star, Capella AA is fusing helium into carbon and oxygen in its core. Capella AB is a slightly smaller but hotter subgiant, about 73 times as luminous and almost 9 times the radius of the Sun, and it's in the process of expanding out to become a red giant. The Capella system is one of the brightest sources of X-rays in the sky, thought to come primarily from the corona of the more massive giant. The second pair of stars in Capella are located about 10,000 astronomical units from the first pair. They consist of 2 faint, small, relatively cool spectral type M main sequence red dwarf stars. The 2 red dwarfs have been designated Capella H and Capella L. Now, almost directly overhead this time of year, a position in the sky known as zenith, we find Canopus, the second brightest star in the night sky after Sirius. Located some 313 light-years away in the constellation Carina the Keel, Canopus looks incredibly bright because it is huge. It's a giant spectral type A white star, with some 10 times the mass, 71 times the diameter, and 10,000 times the luminosity of the Sun. Canopus is another bright X-ray source, also most likely produced by its corona, magnetically heated to several million Kelvin. The temperature is also likely to be stimulated by fast rotation combined with strong internal convection currents percolating through the star's outer layers. No star in our night sky closer than Canopus is more luminous than it, and it's been the brightest star in Earth's night sky during 3 different epochs over the past 4 million years. Other stars appear brighter only during relatively temporary periods, during which they're passing the solar system at much closer distances than Canopus. About 90,000 years ago, Sirius moved close enough that it appeared to be brighter in our night sky than Canopus, and as we mentioned earlier, that'll remain the case for another 210,000 years. But in 480,000 years from now, Canopus will once again be the brightest star in the night sky, and it will remain so for a period of about 510,000 years. In Greek mythology, Canopus was a helmsman and the navigator for the fleet of Menelaus, king of Sparta, which was sailing back from the Battle of Troy. Canopus is said to have died when the fleet arrived at the port of Alexandria in Egypt, and so a star which was visible on the horizon was named in his honour. Now, as we said, it's the brightest star in the constellation Carina, which represents the keel of the boat Argo, used by Jason and the Argonauts in their quest for the Golden Fleece. Located nearby are the vessel's sails, represented by the constellation Vela, and the roof of the boat's rear cabin or poop deck, which is represented by the constellation Pappus. Canopus forms part of the stellar association or asterism known as the False Cross, which straddles the constellations Carina and Vela the sails and is often confused with the real Southern Cross or Crux. This time of the year, the Southern Cross is upside down, low down in the southern skies during the early evening. For our listeners north of, say, Brisbane, it'll most likely be hidden by trees and buildings on the horizon during the early evening. But later on, as the Earth turns, the Southern Cross will rise above the horizon in the south-southeast for our northern listeners and appear to be lying on its left side. One of the best things about living in the southern hemisphere is that most of the brightest stars in the night sky are visible during January nights. Sirius the dog star is the brightest, followed by Canopus the navigation star. Third brightest is Alpha Centauri, the furthest of the 2 pointer stars pointing to the Southern Cross and the nearest star system to the Sun. The 4th and 5th brightest stars, Arcturus and Vega, aren't visible in the southern hemisphere during January, but the 6th brightest, Capella, is visible just above the northern horizon. And the 7th, Rigel, marks Orion's knee. Next, in 8th place, is Procyon the little dog, and 9th is Achernar at the end of the river Eridanus. Finally, there's Betelgeuse, Orion's shoulder, the 10th brightest star in the night sky. So, that's 8 of the 10 brightest stars in the night sky, all visible at once on a warm summer's evening in the southern hemisphere. January also plays host to one primary meteor shower, the Quadrantids. Most meteor showers radiate out from a recognizable constellation, like Leo's Leonids or Gemini's Geminids or Orion's Orionids. But the Quadrantids are meteors that appear to radiate out from the location of the former Quadrans Muralis constellation. In the early 1920s, the International Astronomical Union divided the sky into 88 official constellations. However, that means more than 30 other historical constellations didn't make the cut. The Quadrans Muralis area of the sky falls within the boundaries of the official constellation Bootes. The radiant point of the shower is near the Big Dipper, between the end of the handle and the quadrilateral of stars marking the head of the constellation Draco. The Quadrantids are usually one of the year's most spectacular meteor showers, with up to 8 meteors per hour. They're best seen from the northern hemisphere, and unlike other meteor showers which tend to peak for at least a day or two, the Quadrantids only peak for a couple of hours. While most meteor showers are produced by the Earth passing through debris trails left behind by comets, the Quadrantids are one of only 2 meteor showers known to be produced by asteroids. They're associated with the asteroid 2003 EH1, which is thought to be the remains of a cometary nucleus that fragmented and broke apart centuries ago. EH1 still circles the Sun in a 5.5 Earth-year-long elongated comet-like orbit, which extends out beyond Jupiter. The progenitor is thought to be the comet C1490Y1, which was first observed by Chinese, Japanese and Korean astronomers 500 years ago. It was classified as an asteroid when it was discovered by a near-Earth asteroid telescopic survey in 2003. The only other major meteor shower associated with an asteroid are the Geminids, which occur in December and are caused by debris left behind by the asteroid 3200 Phaeton, which is also thought to be the remains of a comet. Jonathan Nally, the editor of Australian Sky and Telescope magazine, joins us now to continue the rest of our tour through the January night skies.
January night sky. G'day, Stuart. Well, we'll begin with the evening sky because that's when most people are out stargazing. Of course, there are early risers, people who get up early to go to work or whatever, who see the morning sky. The skies are different between the morning and evening because the Earth has rotated and different things have appeared in the east and other things have set in the west. But we'll stick with the evening sky for the moment because, as I say, that's when most people are out and about doing their stargazing. So for us down here in the southern hemisphere, it's summertime, so nice warm weather. You can get out and do some stargazing. Our friends up north and the northern half of the planet have got winter at the moment, so it's a bit cold outside. The saving grace of that, of course, though, is that the hours of night time during winter are longer, so you've got more time to stargaze if the weather cooperates and you don't have clouds and storms and snow and all that sort of thing. But anyway, that aside, what can we see in the skies? Well, we've got the Southern Cross, which is the famous Southern Cross. It's still more or less upside down at the moment, down low on the southern horizon. For most people, it's sort of mid-southern latitudes or further south. As the night goes on, though, and the Earth rotates, the cross will rise a bit higher and higher, and it will end up lying on its left-hand side in the sort of south-southeast. We've got the Milky Way, which is just our galaxy seen from the inside. It's stretching right across the sky from south to north, and its star fields contain some really great constellations and what astronomers call deep sky objects, so nebulae and galaxies and that kind of thing, and star clusters. So starting down in the south, we will start at the Southern Cross, or Crux as it's formerly known, C-R-U-X, Crux, not Crux. Crux is the correct pronunciation, I'm told. Then you've got Carina, Vela, Puppis, which are the parts of the old constellation of Argo Navis. Keep going further along the Milky Way, you get to Canis Major, with its brilliant star Sirius, and then you keep going further up to the north and you get to constellations like Orion, Gemini and Taurus, and all of those constellations have amazing star fields. You've got incredible star clusters and nebulae and stuff. Even a pair of binoculars will show quite a lot of things, but if you do have a telescope or you get hold of a telescope with a friend or a neighbour or whatever, do have a look along the Milky Way. It's just absolutely beautiful, and particularly if, as I say, you're in the south and it's summertime and the weather's good, get outside and take advantage of it. More or less directly to the north, for us here in the south, directed to the north in the mid to late evening in January, there's a tiny clump of stars called the Pleiades, or the Seven Sisters. Now, we've spoken about this star cluster on the show before. It's a group of about 1,000 stars, quite a long way from Earth, but to the naked eye under dark skies, you can see about 6 or 7. Most people can see about 6 or 7, thus the name the Seven Sisters. Some people have claimed to be able to see 10 or 11. And in fact, if you get yourself to the top of a mountain, like a tall mountain, sometimes where they put observatories, where the air is clearer and a bit thinner and you're above all the sort of murk and pollution and stuff, you should be able to see more, in fact. You can see far more up there, up high, than you can down low at sort of sea level. That's why observatories are put up on top of mountains, of course. And in fact, I learned something interesting just recently, or was reminded of something interesting recently, that some cultures in the past have used the Pleiades and a couple of other constellations as tests of visual acuity, to see how good your eyes are. So, if you could see 6 or 7 stars in the Pleiades, you're doing well. If you can only see 5, well, your eyes are not quite so good. If you could see 8 or 9, then you've got super eyesight, that kind of thing. That's interesting. That's a natural sort of test of visual acuity. Yeah.
I see.
So back down the south again, with 2 galaxies that we've spoken about before. You can see with the unaided eye, if you don't have too much light pollution around, such as street light. And these are the small and the large Magellaниc Clouds. They've been famous for many, many years, named after Ferdinand Magellan, of course. Astronomers find them quite handy because they're not too close and they're not too far away in space terms. So they can make out individual stars within these galaxies, which is harder to do with galaxies that are further away. The most famous star that they did make out in one of these galaxies was supernova 1987A, which was a huge stellar explosion in the Large Magellanic Cloud that was spotted on Earth back in 1987, although it happened actually, about 160,000 years before or so. It took that long for the light and the explosion to reach us. I remember going out and seeing that. I got a phone call from a friend. Get outside, there's a supernova in the Large Magellanic Cloud. No one has seen anything like this for hundreds of years. Make sure you see it. I went out.
It was the first supernova of the modern era, wasn't it?
First in the modern era, first since the telescope had been found. Well, the first seen that is visible to the naked eye. Yeah. Plenty of other supernovae had been spotted in distant galaxies for which you need telescopes. but this was the first that was bright enough to be spotted with the naked eye for 400 years before the telescope was invented. And this particular supernova was in another galaxy, the Large Magellanic Cloud. Imagine if there was one in our galaxy, how much brighter it would be. It was bright enough certainly to notice that it was a new star in the sky if you knew the constellations and the stars. Ordinary people in the street would not have spotted that it wasn't that bright. They wouldn't have known that it was a different star that wasn't there the night before. If we had a supernova in our galaxy, then we would really, really, really notice it. It would be very big and bright because it'd be orders of magnitude closer and therefore orders of magnitude brighter than this particular supernova. So fingers crossed we might get one of those one day in our lifetime, although it has been a very long time since one of those has occurred. So anyway, the Magellanic Cloud, if you can spot the Large Magellanic Cloud, there was a supernova that we saw in 1987, although it happened thousands and thousands of years before, that long for the light to get to us. Let's have a look at the planets. So at the moment, beginning of January, low on the western horizon after sunset, we've got Jupiter, Saturn and Mercury in that order of brightness, Jupiter, Saturn and Mercury. Mercury's down low, but it's going to climb higher into the twilight or above the twilight through until about January the 24th. It'll get to its highest above the horizon, not terribly high, and then it's going to sink back down towards the horizon and drop into the glare of the sunset again as it carries on in its orbit around the sun. Jupiter and Saturn are about to disappear into the sunset glare. They'll be gone from our evening sky by the end of January, around the other side of the sun, therefore lost in the solar glare, but they'll be back in the morning sky out to the east, above the eastern horizon next month in February. Speaking of the morning sky, Venus is above the eastern horizon at the moment for sunrise all through January. Can't miss Venus. It's big and bright. Of all the planets that we see with the naked eye from Earth, it's the biggest and the brightest that you can see. So if you're up early before sunrise, you look out to the east, which is the direction from where the sun rises, and you see a big bright white light, and it's not the moon. Well, that's Venus, of course. And what's the last one? We've got Mars. Mars is in the northwestern part of the sky after sunset, looking like it's just a small reddish star. Nothing particularly dramatic about it at the moment. Its distance is increasing from us. Last year we had what was called opposition, which is when a planet is closest to us and therefore appears to be biggest. And Mars is a small planet to start with, so those times of around opposition are the best times to see Mars. And the sort of 2.5 years in between oppositions, it's not terribly good. And in fact, give it a few more months, and even looking through a telescope is not going to do you a great deal of good looking at Mars. Once it gets below a certain point, you really can't even make out a lot of surface detail with a backyard telescope.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. And don't forget, if you're having trouble getting your copy of Australian Sky and Telescope magazine from your usual retailer because of the current lockdown and travel restrictions, you can always get a print or digital subscription and have the magazine delivered directly to your letterbox or inbox. Subscribing's easy. Just go to skyandtelescope.com.au. That's skyandtelescope.com.au, and you'll never be left in the dark again. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.